Hello, we are discussing z-scores and normal distribution. Hopefully you had a chance to print off these notes beforehand. The first page is on the normal distribution, what it is and all that. When we get a whole bunch of data, the more data we get, the closer and closer things tend to be a normal curve. A normal curve is the same, there's criteria to classify it as normal versus bell-shaped. But for our course, we're going to consider bell-shaped as being normal. But statistically, you have certain criteria that you should meet before you classify it as normal. Anyway, bell-shaped curves or normal curves have some characteristics. First of all, they kind of look like that. And the mean is in the center. Mean, median, mode are all, ooh, that looks awful. The mean, median, and mode are all in the center. So there we go, that's a little better. So we call that the mean, right? X bar is the mean. And then because it's symmetric, that means that 50% of the curve is on the left, 50% of the curve is on the right. Now, not only that, but when we talk about the normal distribution, they have, it's symmetric, which I 50 on one and 50 on the other, but it's also got a certain shape in that one standard deviation up and one standard deviation down, it has 68% of the data in that area. Which, if we use the fact that it's symmetric, that means 34% is here and 34% is there, okay? So, and then if we go out 2 standard deviations, so this is now 2 standard deviations, okay? That means that there's 95% of the data in that space. Which, again, if we talk about splitting the curve symmetrically, that means that there's, in this space here, 47.5, and in this space here is 47.5 to make 95. Then we also have 3 standard deviations out. If we look at 3 SDs, that is 99.7% of our data is in that amount of space, which doesn't leave a heck of a lot in these 2 tails, which is why when we look at standard deviation and we look at outliers, we want to look at, how far away from the mean they are. We also call these 3 numbers, I'm right about now, I'm getting somebody saying, is it always 68%? Yes. It's called the empirical rule because all data that is normally distributed behaves the same way, okay? And they also call it the 68, 95, 99.7 rule. Okay, so they also call it like that. So you could look that up on, Khan Academy, or look up the empirical rule on Khan Academy and get the same amount of information. So that covers the first page of the notes. When we talk about percentages within a certain range, we're all going to look at 1, 2, and 3 standard deviations. So, and we're going to use the fact that the curve is symmetric. So if I'm looking at, now I'll do some of the problems with explanation. Now I know you have the problems written out for you, but that doesn't always mean you understand what's happening. So let's say we have the information that they gave you, which was that the mean is 84 and the standard deviation is 3. So if I'm going to draw myself a curve, a normal curve, that means that the mean here is 84. And then if I go one standard deviation up, I'm going to take 84 plus 3. That's one standard deviation up is 87. And one standard deviation down is going to be 81. 84 minus 3. That means 68% is falling in here, the whole thing. And if I use symmetry, that means 34 here and 34 there. Okay. Then if we talk two standard deviations is going to be 84 plus 3 plus 3, or 84 plus 6, which is what, 90? Let me double check my math here. Yep, is 90, although I didn't write it there. So whatever. So 87 plus 3 is 90. And 81 minus 3 is 78. So again, 95 within 78 to 90. If I want to look at splitting that curve, you know, I would do 95, half of 95 is 47.5. Then if I do 3 standard deviations, it's going to be 93. And this one's going to be 70, 5, right? 75. So now the next question that they have is, what percent of test scores fall between 81 and 90? So we're going to use the fact that this is symmetric. So I already said that within one standard deviation is 68. And I said if you take 68 and split it in 2 because it's symmetric, that means there's 34% in this space. Okay? And then if I look at this space, okay, between here and here is 95. Again, we're going to use the fact that it's symmetric and split it in half. 95 divided by 2 is 47.5. So 47.5 in this space. And then to talk about between the 81 and 90, you're going to add those two, which is why I ended up with 81 and a half. Because if I take 47 and 34, I get 81.5%. And that's what we do for like the next one, because we also look at 75 to 87. So from here over to here, that's 3 standard deviations down. 3 standard deviations is 99.7. So I'm going to take 99.7 divided by 2 and get 49.85, which is all of this space in here. Okay. Then if I want for 87 from 84 is this space in here, which happens to be 34%. So I'm going to add these two together and I get 83.85. Okay. So that gives you an idea of what you're doing with this curve. You're breaking it up into chunks. Be careful not to say that this is 34, so this is also 34. That's not true, because they're not, this space here isn't the same. It might be the same width as being 1 standard deviation more, but it's not symmetric up here, or it's not the same up here. So you're not going to have 34 plus 34 plus 34. So be very careful about that. Okay? Then, so that's talking about the normal distribution. Now, let's, for example, take, an argument between two kids. Let's say one kid says, oh, AJ Foyt was the best race car driver ever, da 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 da. And then somebody says, no, Rick Mears was better. These are people in my era. So, if you're watching NASCAR or something, you might have something different. But anyway, but the problem is they grew up in 2 different eras. And because they grew up in two different eras and they had a lot more technology going on in the car at different times of life, right? Eras. You can't really compare them directly. So you have to compare them relative to their era or relative to their time, which is why we're going to talk about Z-scores. Z-scores standardize everything. So it uses the normal curve and says, okay, well, if, this person did better with this group and this person did better with this group, then they might be about the same, or one might be better than the other in a different situation. Towards the end of these notes, you'll see a question on ACT and SAT. And the question is, which one did I do better on? Well, they're on two different scales, so you can't really compare them unless you standardize those scores. Then you can say, yeah, I did better on this one than that one because I did further away from the mean. Yeah, Z-scores have a formula. Basically, you take the data point, whatever it is, X, and you subtract off the mean, and you divide by the standard deviation. And that gives you a Z-score, which is a score relative to your era. So if I'm taking ACT and I find out I did a 25 and the average is 21 and the standard deviation is 10, I can figure out where I am in the pack. Okay. So the problem on page, I think this is page 2 now in the notes at the bottom, it says the mean is 25. So the mean is 25. The standard deviation is 5. And they want to calculate a Z-score for a data point at 39. So you're going to take 39 minus 25, hit equals. It's very important to hit equals here, because if you don't, it's going to take 25 divided by 5, which is 5, and it's going to subtract off. You're going to get something like 34, which is not the Z-score. So you're going to do that subtraction, and you're going to get 14 over 5. So your Z-score ends up being 2.8. What does that mean? That means that your score of whatever this is, data set, whatever they're talking about, is 2.8 standard deviations above the mean, which is pretty darn good. If it's a test score, you're doing fantastic. If it's a temperature, not so good, you're going to die. So, you want to make sure that, you can interpret these things. In other words, 2.8 standard deviations above the mean. There's another one, they talk about temperature. You can look at that. When I look at, the reason why we do this is so that we can compare relative position. Like the discussion, or like the thing I said about, this guy, AJ Foyt was in the 60s, 70s, something like that when I was a kid. Rick Mears was much later. So when I want to compare those two, I have to put them in terms of their standardized score to find out how fast or how good these two drivers were. So, and that's called a relative position. Where are you relative to the pack? Where are you relative to the mean? Okay, so they look at Michael Jordan and they say, okay, my MJ is 78. I'm going to erase this. Hold on. And they're asking who's taller, right? They've got Michael Jordan is 78 inches tall. And for men, the average height of males is 69 inches. And the standard deviation is 2.8. So when I calculate Michael Jordan's, his Z-score ends up being 3.21. When I look at Rebecca Lobo, she has she is 76 inches tall, And for women, the average height, now I'm a little short, but it's 63.6, which comes out to be roughly 5.3 or 5 feet 3.6 inches. All right, so 76 divided by 6.3, and their standard deviation for women is 2.5. So when I calculate Rebecca Lobo's Z-score, her Z-score is 4.96. Okay, so relative to the males, Michael Jordan is very tall, but relative to the females, Rebecca Lobo is taller. So when they ask you who is taller, who is relatively taller, Rebecca Lobo is, because she's relatively taller to the rest of the people, the rest of the women. Okay? And we do this, there's lots of examples on these note sheets. And I tried to do computations off to the side. The hardest thing I think you'll have is not the Z-score or relative tallness or relative shortness or relative who did better and all that. It's going to be the normal curve. And remember, the normal curve, I'm just going to repeat that little bit so that you got it down, so that you can see it right before we leave. So here's a normal curve. Okay? Lots of practice. That's what made me draw these very nicely. Okay. So this is your mean. Actually, X bar is your mean. Okay? If I go one standard deviation up and one standard deviation down, that means that there's 68% here, which using the symmetry, that means there's 34 here and 34 here. So 34 and 34 is 68. Then if I do two standard deviations, that means, matter of fact, I'll do X bar up here. That means there's 95 in this space, which means, now I can't just add another 34. I have to take 95 divided by 2, which means that in this space is 47.5, and in this space is 47.5. Okay? And then, last but not least, yeah, I'm going to use this color. 3 standard deviations is here and here. That means there's 99.7, which if I look from here to here, oops, that one doesn't even write. So pitch that one out for sure. So from here to here is half a 99.7, which ends up being, I don't know those off the top of my head, so I will compute that. 99.7 divided by 2 is 49.85. And that means that the other part over here is 49.85. Now, you will get questions that say, how do I know what's in this tail? Okay, above 3 standard deviations. Well, the whole curve is 100%. If I start from here over, that's 50%. So I'm going to take 100% of the curve and subtract off this half of the curve. That means I only have 50% left. That means I have from here over. Okay? So then if I want to find out what's there, I have to subtract off this piece to find out what's left over. So I'm going to subtract off the 49.85. And that's going to give me what's left over. So if I add that plus 50 and subtract from 100, That means that only 15% is in that tail, which means there's 15% here. No. That seems like a lot. Wait, 1.5%. Now, let's see, 49.85 plus 50 is 99.85 minus 100. That's 0.15 and 0.15. Yeah, because that gives me 0.3. Sorry. Yeah, so it's not even a full percent. It's a 0.15, which means of a percent. So that's a really little bit in there. Sorry, correct that on your notes. So anyway, don't forget you can not call me, but you can text me. We can do a Zoom, an individual Zoom, or we can do a Zoom, as a class. Yeah. Okay? Don't forget, checkpoint 4 was due. You're overdue on that. Checkpoint 5 I'll release tomorrow. Print off all the stuff before you start doing this. Okay? Thanks. Bye.